So this just occurred to me to say this, so this is not prepared. This is improv. It's because Naren was supposed to give today's lecture, and he's just suddenly backed out. I don't know. So last time Aditya gave a crash course on simulating a Markov chain. I'll review that in a moment. But it just occurred to me the second. The previous lecture Aditya gave was on something called stochastic approximation. And I'll remind you what that is. So stochastic approximation is a recursion like this, which looks just like what you have for simulation, as he explained in his lecture. Okay? And I won't review that now. But if this is a linear function of theta, then it's basically Monte Carlo. It's just like what Aditya was talking about on last Thursday. So there's, it's not the proof of convergence of Monte Carlo methods discussed on Thursday is very similar to the proof of this sort of convergence. You set up this algorithm, you have a gain sequence here, which is 1 over n, and you have a function which is a function of the parameter and some noise, which take it to be a Markov chain, maybe a finite state space Markov chain, something nice. So under very general conditions, this will converge to the solution of this equation. Okay? All right. And under much stronger conditions, if you go and scale this and multiply by square root of n, so this error goes to 0. If you scale it up by square root of n, that'll converge to a Gaussian. With the covariance, you can actually compute. If after lecture, if you want, I'll give you a formula. You can actually, there's a formula for this, which is very easy to write down. It's amazing. All right? But only if you construct this algorithm really, really carefully. All right? If you don't design, like put a matrix gain here or something carefully, this sigma will be infinity. It just, it'll just blow up. And examples, Q-learning, what's called TD lambda learning, you get convergence, everyone knows it. But the variance is typically infinity. Typically, I can say that. That was not known until 2 years ago. And actually, while a course like this was being taught here, it was discovered at UF 2 years ago. And it's incredible what this means. I mean, you go and look at plots. And so I was joking with Naren because he was playing around with this yesterday. You plot, say, theta n of 26, D might be equal to, what was it, 80 in your example?
Yeah, 80, yeah.
D equals 80, say. And look at the 29th entry. If you do something like the typical thing that would be done in the reinforcement learning community, you start off here, and you'll see it go like this, and go like this, and go like this, and go like this, all right? And you think, well, it's pretty flat now, it's converged. And if you're a typical grad student, you'll say, hey, advisor, I did it, I solved the problem. But then if you go through and you do something like Zap Q-learning, if you do it right, you just, you can just nail it and almost compute it. It's almost a deterministic problem. So I just have to, I'm so excited about this, Naren did some experiments, but then Shuang just perfected this algorithm last night. So it's really practical. You can either decide to take Watkins Q-learning algorithm and wait 10 trillion samples, or you can take something sophisticated and do it in 1,000, And that's in Google, they're doing this, all right, and UF is doing this. All right. So let's come down to something really simple. So an example of where there's nothing you can do almost. So this is an example, so it's not stochastic approximation, it's just simulation. And we have a MM1Q, remember this boring thing? Okay, so you go up with probability alpha, you go down with probability mu. Alpha plus mu equals 1. This is the discrete time version of the MN1Q. I mean, it looks like the most innocuous thing in the world. And there's something called the load rho, which is alpha over mu. And that's less than 1 if and only if this thing has a steady state, if and only if it's ergodic. Okay, and we saw a week ago that the construction of pi is easy because it's a reversible Markov chain. The detailed balance equations hold. Okay, so you know there's two broad classes of Markov chains which are reversible. One is MCMC. Almost all MCMC algorithms are reversible, and two are a lot of queuing networks, but very special. You know, so if I jumped up by 2 instead of 1, it wouldn't be reversible anymore. The fact that you only go up 1 or down 1 is the reason it can be reversible. I could also have a probability of staying still. But that reversibility would be maintained, but the skip-free property is what's important here. So it's a Born Markov chain, it just goes up or down, and it's got a really nice invariant measure, it turns out. Pi of n is equal to 1 minus rho times rho to the n. So you can really see why you need rho less than 1. All right, if rho was bigger than 1, first of all, if rho was bigger than 1, this would be negative, and this would blow up. That wouldn't look like an invariant probability mass function. So that's invariant. Remember what that means. If x0 has this distribution pi, then xn will have distribution pi for all n. Okay. And so you can compute its mean in steady state. You know, so the expectation of q of t is going to converge to what I'll call the expectation of q infinity. Okay, so basically what I mean by this is the steady state mean of the q-length process. So what you do is you take the probability that q takes on the value n times n for every n. That's how you compute a mean, you know, in noise 1. All right? And that's equal to rho over 1 minus rho, if you remember your geometric distributions. Let's give it a name. Let's call it eta, so I don't have to keep writing this down. And the second moment of a geometric random variable you can work out, it turns out to be twice this quantity squared. And so then you can work out the variance. Okay, and the variance is the second moment minus the first moment squared. So it's 2 eta squared minus eta squared, so it's eta squared. All right. And it's a super nice Markov chain. It's geometrically ergodic. So, I mean, this converges for any initial condition. This mean converges to this at a geometric rate. This converges to this at a geometric rate. People have even computed the rate of convergence. They've, and the variance and all of that. All right. So then here's the question. I want you all to go now and see if you understood Thursday's lecture. We're going to go simulate now. Now, there's no reason to do this, of course, because we know the mean. It's rho over 1 minus rho. But if you understand this simple setting, you'll understand other cases and why things can be really hard. So you're going to go, I'll call it eta hat n. So you basically initialize this thing and then look at these running averages and wonder if your estimates look like that, if they look like that. You know?
What is Q?
Oh, sorry. Sorry. I meant to write X. So I might make this mistake again. So throughout this lecture, it's my bad. I'm just used to writing Q for Q-links and Markov chain. Throughout here. Oh, I did from the start. Okay. I wrote X here, and then I wrote Q here. Q and X are the same thing. My bad. I apologize. Because it's a queuing network. Yeah. So, just a little typo. Okay. Thanks for catching that. Okay. So. Q stands for Q. X means it's a Markov chain. Q means it's the Q length in a queuing network. In this case, a single Q. There's an arrival process to a queue, and stuff comes out. And you can write this as X of t or Q of t. And sorry about the sloppiness. All right. So then we can look at the error, and we can normalize in the same way as this. So we do know the law of large numbers holds. Right? And so we can then talk about the central limit theorem. Look at it. Yeah. So what I was talking about over here, I was actually trying to estimate something that's vector valued, and so this example I was talking about was 80-dimensional, and so this central limit theorem here, it's a multivariate Gaussian random variable. There's a covariance matrix here. So last lecture we just talked about a scalar quantity. The generalization to vector quantities is no big deal. Okay. All right, so we have that. And so the way, it's not completely accurate, but the way to sort of think about this is that like eta hat n is equal to eta. So divide both sides by square root of n plus sigma q over square root of n w This is truth. This is interpretation. Okay? So you put this in an exam, you get full marks. You put this in an exam, you lose a few points. All right? But this is hard to see, and this is easy to see. This is a way to think about it. It's basically my true guy is reality plus a scaled, standard Gaussian random variable divided by square root of n. All right? Because this is this times this has this distribution. So there's an approximation in distribution. It's not really true because this is a thing that's close in distribution to a Gaussian, to W. This is going to 0. I've got 0 is approximately, this is going to a constant, which is this. That's going to 0. To make sense of this, you have to look at this, right? Do you see what I mean? This has a well-defined definition. Convergence of distribution, right? This is a hokey way of just thinking of trying to interpret this.
Would you ever code that one up?
It's meaning, there's nothing to code.
You couldn't use it in a simulation?
None of this can be used in a simulation. Or how can it be? Nothing about coding. How do you, that was my question. So, given what I just wrote down here, how long do you have to wait to get a good estimate? So that's the reason for the CLT, is thinking about how long do you have to wait. So that's the point. I mean, the reason for writing this way is it's really clear how long you have to wait. That should be small, right? So square it, n has to be a lot bigger than sigma squared q. So I gave you a question, there's an answer. Give me an n, somebody. Is it on the board? I'll be back in a minute. Somebody's going to be brave enough to tell me their estimate of n. I'll give you a row. Okay, 0.95, this means that 5% of the time the queue is idle. So basically 1 minus rho is the steady state fraction of time that the queue is empty. So a 95% utilization is what you might want in a healthy economy, you know. All right, I want somebody to tell me what n is when I get back. I'll be right back. Now, what you say, you'll be wrong. But be brave anyway. Just tell me what a guess.
Trillion.
A trillion. You're right. That would do it. But what have I not told you? I left out a very important piece of information. What? No, what? Yes. Did somebody think that they had sigma q? You did, okay. Yeah, I'm not mad at you, you're brave. I'll bet half of you thought sigma q was on this blackboard. Is sigma q anywhere on the blackboard? Does anybody see sigma q?
Theta squared.
What is sigma q? Anybody remember what sigma q is from last lecture? I don't blame you if you don't remember. So it's not always true, but in this example, you can take the second moment of this quantity, and it will converge to that. Now, it's not true, you know. Convergence in distribution does not imply that, you know. I think Aditya screamed that last lecture. So we know I'm sorry. That's a stupid way of writing it. How about this? Yeah, this is how to write it. Or, I mean, yeah. So, this thing here is a thing we're calling approximately Gaussian random variable. And if I divide it by sigma q, it's approximately a standard Gaussian. I just want to, it's worth saying this loudly again. This is equivalent to convergence and distribution. There's a lot of ways of stating it, but this is maybe the most intuitive. That this random variable convergence and distribution to that, if for every bounded and continuous function, the expectations converge. I know that normally you write this in terms of cumulative distribution functions. I think that's more intuitive. Sometimes you can extend to non-bounded functions, and it's very typical that you can, and in particular here you can. So in this case, it does turn out that it's the expectation So basically, I'm taking h to be the whole thing squared. That's not bounded, but it does turn out to be true in this special case, all right? There's very, very general conditions for that. And that, as Aditya showed, is a sum n equals minus infinity to infinity of r sub q of n. It's the sum of the autocorrelation function, all right? And just imagine this Markov chain, how highly correlated it is. If I'm big, in the next step, I'm one q length bigger or one less. It's insanely highly correlated. If you plot R of n, you get the variance here. That's pretty big. Eta squared is, rho over 1 minus rho squared, which in this case is fairly large. But then it crawls downwards. And it's symmetric, And I mean, you can come up with a recursive relationship. I think this is rho times this or something. Isn't it? I think it's geometric in a row, So it's huge, 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 huge. And guess how huge it is? Anybody have a guess? Yeah.
Should that be 8 a.m. hat? Should that?
Oh, did I have a hat somewhere? 8 a.m. Oh, there's a hat there. Yeah, I had hats. There's no 8 a.m. without a hat. Yeah. So what do you think sigma squared q is? What's I don't remember. Well, there's a half in there, so things get shrunk a bit. And do you think it's like this? Probably not, because you're summing a bunch of things that are very, very similar. It turns out it's 1/2 times eta, not squared, not cubed, but to the 4th power. there's some error term that's much smaller. This is for rho close to 1. All right? And that's, we're talking about rho close to 1, and eta was rho over 1 minus rho, so rho is close to 1, so it's like 1 over 1 minus rho. Right? And in my example, 1 minus rho is 0.05, and what's that? That's 1 over 20. So it's 20 to the 4th over 2.
Yeah, I think earlier in class or something, like one day someone...
That's big. and it's not, doesn't have to be, n doesn't have to be greater than this. It has to be a lot bigger. If you take n equal to this, you're going to be left with this Gaussian error, and that could be significant. It could be, you could see big things jumping around. So, I think it's a lot bigger than that in practice. What is that? That's, it's like 10 to the 5th, I guess. 2 cubed is 8, and so it's close to 100,000. But you go check it out. You simulate the MM1Q. You're going to find that's nothing. After a million samples, you feel like you've gotten nowhere. It's just impossible. So imagine something this simple and you can't simulate it. It's sad. So Monte Carlo techniques have to be handled with care. There are ways to deal with it. You could take a whole course on this. And actually, this last chapter of my Netbooks book has a whole menu of tricks to try to deal with this. One more thing. So anybody have an idea what this would look like? So remember when we were talking about simulating IID random variables and we had Chernoff's bound, right? So you expect this to be some minus I of epsilon, Well, guess what I of epsilon is? You could ask another question. What about? So this is the probability of your estimate exceeding having an error of epsilon, and here's epsilon the other direction. All right. Now remember, we're averaging something positive, so the probability of a large negative excursion is pretty unlikely. It's always positive, right? But it could get really big, and if it gets big, it stays big, right? If you have some excursion and it gets up to, the mean is 100, but it gets up to 1,000, well then I erased it. It goes down only one step at a time. So it doesn't recover from a large event. So you can plot I of epsilon. And it looks very pretty and convex, like that, And it blows up at minus eta because if epsilon equals eta, you're asking the probability that the average Q length is negative. Pretty unlikely, right? What's the probability that this is negative? Right? All right. So over here it's like that, and then positive epsilon. it's 0. So it turns out this is 0. So it's got this really strange behavior. You're very likely to overestimate the mean, and you're not likely to underestimate it. And when you look at a histogram of this, if you look at a histogram of what I called here W hat n, yeah, it's going to look like. So here's a Gaussian bell curve. And if you so basically run this, take n equals 10 million, run it for 10 million samples, do it again, independent samples 100,000 times, all right? And then you could just draw a histogram of use the hist command in MATLAB, and you get a histogram, and you get something really funky. It's going to like distort off to the side a bit, and you're going to see some big heavy tail. The Sentiment theorem takes a long time to kick in. It's very slow. It's got a heavy tail on one side and a light on the other. It's really pretty. So the simplest Markov chain in the world, and it's a minefield. Yeah. I can't. It's only the fact that if I get big, it takes a long time to recover, because it can only move one step at a time. All right. And when you're summing, you're compounding that problem. Basically, the sum is like the integral under a curve, area under a curve. And so whenever you're big, that contribution, that largeness carries on for a large time. Yeah, it's always 0, no matter what epsilon is. It's for epsilon positive, of course. In both cases. Yeah, it's really wild. So that's a fairly new result, and there are ways to fix it. One solution yeah. So one thing you can do is you can take your estimator and you can tack on, and actually hold on a second. You can add on an average of something which you know has 0 mean. And for Markov chains, there are lots of functions like that. I'm not going to give examples right now, but it's very easy to cook up functions of the Markov chain that have 0 mean, but you know have 0 mean. It's really easy to do that. And then you could basically have a tuning parameter here and tune theta here so you minimize the variance that's appearing here. And if you're really clever, you can completely solve the problem. All right. Again, but that's a research direction. We close there. All right. Unless there are questions. Yep.
Why do you have an equality constraint in both cases? So is there greater amplitude and lesser amplitude?
Now this is the large deviation. Like this would be for ID processes. This is Cramer's theorem, and we know that this is obtained by that. Look at the log moment generating function. Yeah. But here,
Equality constraint in both cases, right? Why should be greater amplitude and in the other case would be less than, right?
that's what I wrote down.
Equality constraint.
No, their equality. That's what we have for Cramer's theorem.
Well, I'm talking about the probability.
Yeah, but look at the probability
Right.
that you exceed the mean by epsilon. That was what we did in Cramer's theorem and Chernov's
I
bound.
understand that. I saw that, but
So there's an upper bound, and then there's a lower bound, right? There's a probability of being bigger than the mean. There's a probability of being less than mean.
okay.
Yeah. Right. Yeah. Is that clear? I mean, that's no. So if the Q's YID, then we would have a really pretty formula for this and this, and they'd both be positive. You know, if they were IID, so right now we know the steady state is geometric. If we just averaged IID geometric random variables, we would have a beautiful clean formula for I of epsilon. You know, yeah. Oh, you don't like the use of the same symbol for, yeah.
It's the probability part, but I'll ask later.
Okay. Yeah. Well, we know this converges to eta, so this should go to 0. You know.
Right, I guess my question is, why do you have greater than or equal to, then less than?
Oh, yeah, no.
Shouldn't one be like greater than or equal to, and the other case would be less than?
Yeah, they are greater than and less than, right?
Right, so, but why do you have the?
No, I'm looking at the both. There's two questions I want to ask. What's the probability that my estimate exceeds the mean, the true mean? And the other question is, what's the probability my estimate is less than the true mean? They're both good questions. And both of these go to 0, right? But it turns out this goes to 0 at a much slower rate than this does. You know? It turns out if I divided by the square root of n, I would get a finite limit. Yeah. It turns out that's the right scaling for the exceedance probability. If I divided by 1 over the square root of n, I wouldn't get 0. Is that okay? Is that clear enough? Okay. All right. So this is, so I swear to God, everything we've done in this course has been practical. I know there's been a lot of mathematical fluff. I stand by it. I always think about, should I get rid of measure theory? I can't.